Before we talk about the young double slits, right, or sometimes just called as the opening or the aperture, so it's just synonym if you have the same meaning. So let's talk about when we have the a plane wave, right, and then passing to a hole first. Okay, so this hole or slits or opening or aperture, so we just have the screen, okay, to block the plane wave, and we have a small hole here that will let the wave passing through it. So in this case, you can see that if the wavelength of the incident wave, so from this picture, what is the wavelength? The wavelength is the distance between the wavefront. Okay, so now you can see that this will be the wavelength. So if the wavelength is much less than the size of the hole, okay, this is the size of the hole. So now you can see that the wave will just continue its path and go from the left and then to the right. But then on the other hand, if the wavelength is about the same size as the size of the hole, okay, with this picture, this is the wavelength and this is the size of the hole, right? Just the same thing. So the wave will be diffract in some direction, right? In some direction. But then finally, if the wavelength is much larger than the size of the hole, so you can see that this size of the hole is very small compared to the wavelength. So it will generate, okay, a cylindrical wave if we have the slit, or it will generate the spherical wave if we have the hole here. Okay, so in this case, we can say that the opening behave as the point source emitting the spherical wave. Okay, if you look at this one as the point source, so we can have the spherical wave here. So, young double slits. Okay, for the young double slits here, we just want to consider in the case that the wavelength is much larger than the size of the slit. Okay, the wavelength is much larger than the size of the slit. This is going to be the young double slit. But then later we talk about the diffraction by double slit, right? So in this case, the wavelength can be about the same size or less than the size of the slit. Okay, so it's going to be in these two cases. So we'll talk about this one later because we need to take into account the diffraction by the wave as well. But now for this one, we just think that the slit is the point source. So we can just consider only the interference of the wave. Okay, this is going to be the experimental setup of the young double slit. So the first thing we have the monochromatic light. Okay, so don't forget that the monochromatic, it means that the wavelength is constant, right? Because the chromatic just mean the color, and the mono here, sorry, the mono, it just mean one. Okay, so it means that one color is one wavelength, right? Because for each color we correspond to each wavelength. So it means that when we have the monochromatic light, so we will have the single wavelength light. Okay, that's to be the meaning of the monochromatic. Okay, and then if we have the monochromatic light passing through the slit, so now this slit again, so if the wavelength is much larger than the size or the width of the slit, so we can think about the slit as the light source, not the point source. Okay, the point source is here, but now we can think about the slit as the light source, so with the source align as a line. Then we can have the cylindrical wavefront from the left and then propagating to the right, and then we have the double slit. Okay, so this will be the double slit that we are considering. Then so the wave will propagating through the slit, right, and it will generate the two cylindrical waves. So now these two waves are coherent to each other. So that's why you can see that this will be the objective of this setup, because these two slits will generate the two waves with the phase difference must be constant because it just comes from the same wave here, right? So that's why these two waves here we have the phase difference to be constant. Okay. So now the two waves from these two slits, right, or from the slits, if you just interfere to each other on the screen, so we have the screen here, and then we can have the pattern to be the maximum and the minimum, the maximum and the minimum, and etc. Okay, so you see this is the maximum, the minimum, maximum, minimum, and the maximum, and etc. Okay, so now the maximum one is just called the bright bands or the bright fringe. Okay, sometimes just called the bright fringe, FRINGE. And okay, the dark bands is all the dark fringe, just the same meaning. Okay, so this will be the experimental results that we can get. Okay, so look at another features. Okay, from this one, this is 0. Okay, let me just put it here, and then let me make it as the dashed line. Okay, and let's say that if we have a slit, right? Actually, let me move. Okay, this would be better. Okay, if I have a slit here, okay, so this will be my slit, and then this one as well. Okay, just look the same and duplicate. Okay, okay, so we have the screen and we have double slits, right? And then if I have the plane wave, okay, if I have the plane wave, so now you can see that I'm trying to draw that the wavelength is much larger than the size of the slit, right? So we have the wavelength here equal to the lambda. Okay, so then you can see that on the screen. Okay, this is our screen. You can see the bright fringe and the dark fringe. Okay, the bright fringe and the dark fringe, the bright fringe and the dark fringe. Okay, so we know that the bright fringe just correspond to the constructive interference. Okay, the bright fringe correspond to the constructive interference. It means that the wave from these two slits, right, will sum up together and then form something like this one. Okay, all this one. So that's why we can get the constructive interference here. But then on the other hand, for the dark fringe, we can it will come from the destructive interference. Okay, the dark fringe. Also, this one is the dark fringe, the dark fringe, the dark fringe, and etc. Just come from the destructive interference. It means that the two waves sum up together and then finally cancel to each other. Okay, so this one again, the destructive interference, right? If we define here, okay, if we define, let's say that this distance, if I consider any, the order Okay, and then we have another line. Okay, so now let's see. Okay, so let's consider this one. Okay, so now you can see that I have the three lines. The first one just come from the slit and then to the point of interest, from the slit to the point of interest, right? And yet the second one is be from the center of the two slits and then to the point of interest here. Okay, if we define here, if this angle to be equal to the theta and then sub m, okay, and now this m, right, is going to be the order. For example, this will be the zero order of the bright fringe. So this will be the first order of the bright fringe, the second, the third, the fourth, and the fifth orders of the bright fringe, etc. Again, we can have the order equal to the 1/2, the 3/2, the 5/2, the 7/2, and the 9/2, right, of the bright fringe as well. Of the dark fringe as well. And then let's say that if the distance between the two slits here equal to d, okay, equal to d, and then the distance from the slits and then to the screen equal to the L, and then this distance from the central maximum and then to the point of interest equal to the yn, okay, equal to the yn. Let me say something. So the central one here, right? We have the central bright fringe is called the central maximum. Okay, so this order is just called the central maximum ก็คือความสว่างก็คือค่าสูงสุดที่ตรงกลางนั่นเอง central maximum. Okay. Then we can have the relationship between these variables to be, okay, the d psi theta m, okay, theta m. This is for the bright. No, let me just write. Okay, let me okay, write in the other way. D psi theta m equal to the m and then times lambda. Okay. Oops, sorry. We have this equation. The sin theta m equal to the m times the lambda, where, okay, m equal to, if the m equal to the 0, equal to the 1, 2, 3, and etc. This is for the bright fringe. Okay, this is for the bright fringe corresponding to the constructive interference. Okay, but then if we have the m equal to the 1/2, the 3/2, the 5/2, and etc., this for the dark fringe corresponding to the destructive interference, and that's it. Okay, actually this equation can be simplified. Okay, we can simplify to be, if the yn, okay, if the yn, this is the yn, the distance from the central maximum to the point to the mode of interest, right, is much less than the L. Okay, is much less than the L. We can simplify to be the ym. Sorry, actually I use m, not the n. My bad. Okay, m. Okay, if the we can get that the ym is equal to, is equal to the m times lambda times the L, and then over the d. Okay, the m times lambda times the L over the d. So this will be the case. Okay, this will be the case. And then moreover, we can find the neighboring bright fringe. Okay, let's say this one, delta y. Okay, we can find the neighboring y fringe, right, to be. Okay, so let's say that if we want to find delta y, what is delta y? Delta y is, let's say, the y of the m plus 1, right, and then minus the ym. Okay, so then it's going to be equal to we have the m plus 1 and then times lambda l over the d, and then minus the m lambda l over the d. Okay, if we subtract to each other, we can get that delta y is going to be equal to lambda times the l and then over the d. Okay, so this will be the distance. Oops, sorry. This is going to be the distance between the two closest fringe. Okay, it means the bright fringe to the bright fringe or the dark fringe to the dark fringe. Okay, let me just specify. The bright to bright, or from the dark to dark. Okay, from bright to bright or from the dark and then to the dark. Okay, so one thing that we can get from this question, right, is that the distance between the two bright fringes must be constant. So that's why from this picture you can see that we have from this to this is one distance, and then from this to this is another distance, right? So this distance and this distance just the same. Okay, because this question it just depends on the wavelength, the L and the D. Okay, it doesn't depend on the M. So that's why the distance between the two closest bright fringes are the same, always the same. Okay. Okay, so now I just want to derive this equation for you guys. Okay, how can we get this equation, right? Let's just derive this one. Okay, so now from this picture you can see that if I move the screen, right, this is the screen. Okay, actually I should write down this will be the screen. Okay, if I move the screen, I mean further and further, so that's be the case that we just want to consider, because in the real experiment this L is going to be equal to about 2 meter or 3 meter in the real experiment. Okay, this L just about the 2 or 3 meter, but now for this Y it's just about millimeter. It means that the distance difference between the L and the Y just about 1000 times, etc. Okay, so that's why you can see that if I move the screen to the right hand side, it means that the L is much larger than the Y. So it means that these three light rays will be parallel to each other. Okay, does that make sense? If I move the screen to the right hand side, so these three light rays seems to be parallel to each other. Then I can draw something like one duplicate, 2, and then 3. Okay, 1, 2, 3, and here we have our slit. We have our slit here. Oops, let me okay. Okay, this will be our slit. And don't forget that the center one is the dashed line. Okay, corresponding to this one. And we have this line right? Sorry. Okay, it's gonna make angle to be the theta m as well. Okay, so it means that okay, let me just write here. It means that if this angle to be theta m, so this two we make the angle to the horizontal axis to be theta m as well, right? So now we just want to find the phase difference. Okay, the phase difference between these two light rays. How? Let me draw one line. Okay, so let me draw one line here. So this line will be perpendicular to another light ray. Okay, so now you can see that the phase difference between these two light rays, it just depends only on this part. So why I say that? Because this light and this light we have the same length. So when it just go to to the screen here, right? So this light and only this part we have the same length. So the phase difference between this light ray and this bright ray will be only this part. Okay, so this can be the phase difference. Let me just use as the delta for the phase difference, right? The same thing as we have we talked in this topic, right? The delta here. And we know that this part, this part we have the length equal to the d. Okay, so the d here just the separation between the two slits here. If this angle equal to the theta m, it means that this angle, okay, this angle equal to the theta m as well. Then you can see that we have this triangle. Okay, we have, oops, sorry. Okay, we have this right triangle. We have this right triangle, so this 90 degree, and this angle is going to be the theta m. This is the d, and then this is the delta. Okay, then we can find the relationship between the delta and the d to be the delta just equal to the d psi theta m, right? Equal to the d and then psi theta m, because if we break the d of the angle, it's going to be equal to the delta here. So delta equal to d psi theta m. But don't forget that this delta is the path length difference. Okay. So now to get the constructive interference, for example, the bright fringe, it means that this delta must be equal to the 0, lambda, 2 lambda, 3 lambda, and etc. So it means that it must be equal to the m times of the wavelength, and that's it. Okay, so that's why we can just get this equation from this picture here. But now if we just want to get the portion of the dark fringe, right? Okay, so we know that the path length difference equal to half of the lambda. So that's why we can say that when the m equal to the 1/2, 3/2, lambda half, we can get the dark fringe or the diffractive interference. Okay, so this will be our derivation here. So next thing is, if I just want to derive this equation, okay, we need to use some approximation. So let's say that if the ym is much less than the L, okay, so if we look at this triangle, okay, if we look at this triangle, if the ym is much less than the L, it means that okay, so let's this triangle. Okay, this is be the theta m and the ym and then the L, right? So now you can see that this length, right, the hypotenuse equal to the ym square and then plus the L square. Okay, then we can get that the sine theta m is going to be equal to, okay, opposites and then over the hypotenuse, right? So sine theta m is opposites and then over the hypotenuse. So we have the L. Oops, sorry. No, my bad. I just made switch to each other. Oh, wait. My bad again. This is L and this is YM. Okay. So the opposite is the YM and the hypotenuse is the square root of the YM square and then plus the L square. Okay. I can be equal to the YM over the L and then the 1 over the square root of the 1 plus the YM and then over L and then square, right? So in this case, I just bring the L out of the square root, so that's why we can get the YM over the L and total square here. Okay, so now we said that if the YM is much less than the L, so it means that this term will go to the 0, right? Because the YM is much less than the L, so this guy go to the 0. And then finally we can approximate to me the YM and then over the L, and that's it. And then okay, we can just sub the YM over the L, right, into this equation, and then finally we can get this one. Okay, one thing that I just want to emphasize about this question is in the experiment this question is easier to use, because this question we can just measure the position of the bright fringe, right, or the dark fringe. So that's why I say that this question is much easier to use. But now from this question you need to measure the angle. Okay, it's called the diffraction angle. Okay, diffraction angle from the central line here. So in the experiment this can be quite